Welcome back. So we have been talking about dimensionality, and the way I want you to think about dimensionality is basically we are asking the question, what is the least amount of information necessary to fully specify your location? So as an example, we said think about the number line. If the number line is a 1D object, if I know you're somewhere standing on a number line, I could just ask, what number are you next to? You give me a single piece of information, just the value of that number, and then I know exactly where you are on a number line. If you're somewhere on a 2D sheet, I just need to know where are you in the left-right direction, where are you in the up-down direction, and then I know exactly where you are. So I could think of left-right as having its own number line that I call X. I could think of up-down as having its own unique number line I call Y. So X and Y that you used in grade school math is kind of really just saying we have two number lines. Every location on that sheet will have its own value for X and its own value for Y. That's just two number lines. It's nothing more than that. So we talked about a sphere, and a sphere is kind of an interesting object to think about, because a sphere is now a curved surface. So if I'm standing on a sphere, I could say, well, I could talk about up, down, left, right, front, back for my sphere, but because I'm constrained to stand on the surface of the sphere, I'm not allowed to dig onto the center or jump off the sphere. I could actually describe a sphere as being an inherently two-dimensional object. You just give the latitude and longitude of your location, and you know exactly where you are standing on that sphere. So, now, taking these ideas and moving forward, I could say an arc is a 1D object, because an arc is, for all intents and purposes, identical to a number line. Just imagine you have a number line, but it's made out of rope. So I could take my number line and I bend it. I still only need a single number to specify my location on that arc. So from this point of view, I could think of an arc as a 1D object. And similarly, the surface of the Earth is a 2D object. No matter where you are standing on the surface of the Earth, if you give me your latitude and longitude, I will know exactly where you are. So, in 3D, we often will sometimes work with X, Y, and Z because mathematically these coordinates are just things that describe your location. Mathematically, X, Y, and Z is often convenient to work with, but this isn't always what we want to do. So X, Y, Z usually refer to the left-right direction for X, the up-down direction for Z, and the in-out direction for Y. But sometimes we could use something a little bit more convenient. So to describe my location anywhere in the universe, I could say, with regard to some reference point, how far up, down am I, above or below that reference, how far left or right am I of that reference, and how far in front of or behind that reference point am I. But sometimes it might be nicer to work with something that is often called spherical coordinates. So instead of thinking of X, Y, Z, I want to talk about this R, theta, and phi. So here's my R, here's my theta, and here's my phi. Let's pretend we are standing on the surface of the Earth. Now let's pick any star in the universe. Don't pick the sun. Pick your favorite star in the universe. Now, somewhere on the Earth, that star is going to be directly overhead of you. So maybe you have to go to Saudi, or maybe you have to go to Namibia, or maybe you have to go to Germany or Brazil. But somewhere on the surface of the Earth, that star you picked out is directly overhead of you. Okay. Well, I could think of the location of that star in the sky kind of as my latitude and longitude. So if I think of theta as being my latitude and phi being my longitude, then I could fully describe the location of any star in the universe as just saying, at what latitude and longitude would I have to go on the Earth if I want that star to be directly overhead? And then I just ask, how far away is that star? So sometimes we could take three numbers to describe any location in the universe in terms of x, y, and z. Or sometimes we could take any location in the universe in terms of r, theta, phi. And both of those are completely valid ways to describe your location anywhere in the universe. Now, I did intentionally say star. You could ask, well, what if we wanted to describe a location below the surface of the Earth? Okay, then we'll just say, we'll pretend we begin at the core of the Earth and we're moving outward, so the surface of the Earth is above us or something. But what are some consequences of this? Or why am I bringing this up? Well, I'm going to call back to the Pythagorean theorem I talked about before. So on a flat sheet of paper, we said a squared plus b squared equals c squared. But I'm going to write the distance between two locations could be written as s squared is equal to x squared plus y squared. So all I'm doing is I'm saying the horizontal distance I will call x, the vertical distance I will call y, and the diagonal part of my triangle, the hypotenuse, I will call s. So instead of a, b, and c, I am using x, y, and s to describe the lengths of the side of my triangle. I'm not really doing anything different than what I had in the previous slide. I'm just changing the symbolism of the letters to match what I'm going to be writing more often. Now, in cosmology, what we would say is we would say the line element connecting two adjacent points on a flat 2D sheet is given by ds squared is equal to dx squared plus dy squared. So the only difference between the usual Pythagorean theorem that could apply to a triangle like this and what I wrote here is we usually want to use very teeny tiny quantities, because if I could take any arbitrary curve and I could imagine any curve at all, whether it's very interesting or whether it's just a simple curve, as many really small steps. So I will describe a really small hypotenuse is equal to a really small x squared plus a really, really small y squared. And obviously then the length of my hypotenuse will be small, so the two corners of this triangle will be really close together. So ds, and this term ds, the separation between 2 points, is going to be the separation between 2 points that are very close together on a flat sheet. Now, if we want, we could also talk about the separation between locations in 3D. So the Pythagorean theorem in 3D looks very similar to the Pythagorean theorem in 2D. So instead of talking about the separation on a flat sheet, I'm now going to talk about the separation between here and here, between 2 points in a grid of some sort. So in a 3D volume where I have 3 directions I could move around in, I could write the separation between 2 points as s squared is x squared plus y squared plus z squared. And if I want to talk about the separation between 2 points that are really, really close together, I would say ds squared is dx squared plus dy squared plus dz squared. So the separation between 2 points anywhere in 3D could be written like this. The separation between 2 points that are really, really close together is going to be written like this. The d essentially stands for a really small, minuscule distance. Why am I bringing this up? Well, often it is said that a straight line is the shortest distance between 2 points, but for the context of cosmology, I would rather change this reasoning around. I would rather say the shortest distance between 2 points is what we call a straight line. Now, by saying that, what I'm essentially saying is usually you imagine, okay, we take a sheet of paper, we connect 2 points, and we draw a line between them, and the straight line is the shortest distance. But I would rather say the shortest distance is going to be a straight line. So I could connect 2 points with a bunch of different paths. I measure the distance of all those paths, and whatever path is the shortest, that is what I call straight line. Whether the path between here and here might be just the straight line like normal, But perhaps for the universe decides to go all crazy and the shortest distance between two straight lines between 2 points might be something more curvy like that. If I happen to measure that that is the shortest distance, then I will say that is what is a straight line. And one example where this applies very directly is on a curved surface. So on a curved surface, not a flat sheet of paper anymore, the smallest separation between 2 points is going to be some type of curved line. And this is what happens with airplane flight paths. Now, airplane companies, they would rather save fuel because that cuts down on their business expenses. They can make the plane tickets cheaper if they don't have to buy as much fuel. Say you want to fly from London to Shanghai. So that would be a really long flight. If you've ever flown across continents, those flights are absolutely awful. Well, London is closer to the North Pole than Shanghai. So if you're going from London to Shanghai, you overall are traveling south. But the thing is, when you're leaving London, you're going to actually leave London traveling northwest rather than southwest. And the reason for that is because when you're traveling over the surface of the Earth, you are actually traveling over a curved surface. So the shortest path along the surface of the Earth that connects London to Shanghai is not just a straight line drawn something like this. The shortest path from London to Shanghai, when you're restricted to traveling on the surface of the Earth, is actually some type of arc. And this principle that the shortest distance between 2 points is a straight line, but no longer what we intuitively think of as a straight line, also applies if we're traveling, for example, on the surface of a donut or on some more interesting curved surface. So, we could talk about the line element on the surface of the Earth. So if we're traveling on a sphere, we could describe our location with latitude and longitude. And the separation between nearby points on a sphere is going to look something like this. We have some term that talks about a slight change in latitude. We have a term that talks about some small change in longitude. So the separation between two very nearby points is going to look something like this. Here, r is the radius of the sphere that we are traveling on, because the distance between points on the Earth is going to be different from the distance between points on a baseball. Probably the Earth will be much bigger because the Earth is much bigger than a baseball. So this term r just allows us to account for the fact that whatever sphere we're traveling on, whether it's the surface of the Earth or over the surface of a baseball, that could affect the distance between 2 points on that sphere. Now, if we are going to be traveling around the surface of a donut, we have another way that we could talk about the separation between very nearby points. So the separation between nearby points on the surface of a donut looks something like this, where C is basically talking about the size of our donut. So how big is it from the center of the donut to the middle of the doughy deliciousness? A is something that tells us about the thickness of our donut. Is it really skinny and small, or is it a nice thick donut? Now, U and V are actually our locations on the donut. Are you near the inside part of the donut, the outside, top or bottom? U could be where are you around the donut. So if we're restricted to walk around the surface of a donut, the separation between two nearby points on a donut will look something like this. So the take-home message of the past few slides is you don't need to remember any of these equations, but the separation between locations on a surface depends very much on what is the shape of that surface that you're moving around in. If you're moving around just on a flat sheet of paper, the separation between 2 points on that paper is basically the Pythagorean theorem that you learned about in high school. But if you're moving around on the surface of a sphere, or if you're moving around on the surface of a donut, or there are some other possible types of surface you can move around on, then the separation between nearby points will take a different form.